How many positive odd numbers less than 100 have exactly 4 factors? Now, the good thing about team is that if all else fails, you can have someone that's a member of your team just go through all 100 numbers and see if they can find how many of them there are. But I want to show you a nice and easy way to go about this problem. And in order to solve this nicely, there's an important fact that I want to tell you guys about. So this fact will have to do with counting the number of factors that a number has. Counting the number of factors. So there's a very nice trick, and you have to use prime factorization first. So the first step, you take a number and you have to write it as a product of its prime factors. So for example, if I take 12, I know 12 is not prime because I can rewrite it as 2 times 6. And 2 is prime, but 6 is not. So I can also write 6 as a product of its factors. And in this case, all of these numbers are prime. So the prime factorization is going to be the product of these numbers. And another way you can write this is like this. So this tells me that there are 2 2s and there's 1 3. Now, the trick is in order to find the number of factors a number has, you take the exponents, which are the numbers on the top, and then you add 1. And then you have to add 1 to each of them. And then you multiply them together. So in this example, we have 2 exponents. We have 2 and we have 1. So this 2, we're going to add 1 to it to make 3. We're going to add 1 to this to make 2. And the last step is to multiply all of these numbers together. So if you multiply them together, then you get 6. So 12 has 6 factors in total, and you can write them out. These are the 6 factors that 12 has. So now let's use this trick that we've just learned to solve this question, because we need to find the numbers that have exactly 4 factors. So there are some cases that we need to consider. The first case is when we have a prime number raised to the 3rd power. And there's another case where we have one number raised to the 1st power times another prime number raised to also the 1st power. So if we apply our trick to these numbers, we take the exponents and we add 1 and we multiply them together. And you'll see that in both of these cases, we're going to get 4 factors in total. And you can check that these are the only 2 cases of numbers that will work. So let's first focus on the case when our number is a prime number raised to the 3rd power. So this will include numbers like 2 to the power of 3, 3 to the power of 3, 5 to the power of 3, and so on, where these are all prime numbers. Now, we know that from our problem, it's only asking us to find odd numbers. So 2 to the power of 3 doesn't count. 3 to the power of 3 equals 27. So 27 is less than 100. So this is a number that counts toward our total. Let's not circle that. Let's just box that to show that that's one of the numbers I'm including. And 5 to the power of 3 is more than 100, so this does not count. So in the first case, the only number that we should count in our total is 27. So let me write that off to the side here. So there is one number that satisfies the first case. Now let's look at case 2, when we have one prime number multiplied to a different prime number. So there are going to be more there are going to be more possibilities here. And in order to do that, let's take a look at all of the prime numbers. And there are going to be a few of them, but they don't have to be too big. I'm going to just list a few of them and then I'll stop. Let's say right there. Let me make sure I didn't miss any of them. 21. Okay, I think that should be all of them up to 31. Excluding it, and we're not including 2 because remember, we want our number to be odd. So I'm going to start, say, with 3, and I want to find the largest prime number that I can multiply to 3 that will give me a result less than 100. And in this case, 31 is the largest number where the product is less than 100. So if I take 3 times 5, 3 times 7, 3 times 11, all the way up to 3 times 31, all of these numbers are going to have exactly 4 factors. And you can count how many of them there are. Looks like that there are 9 of them in total. So there are going to be 9 of these numbers where 3 is a prime factor. Now let's take a look at numbers where 5 is a factor and we don't have 3. So if 5 is my smallest factor, then I have 5 times 7, excuse me, 5 times 11, 5 times 13, 5 times 17, and 5 times 19. And if you add those together, in total, there are going to be 5 numbers. All right, looking good so far. And what if our smallest factor, prime factor, was 7? In this case, 7 is going to have 7 times 11 and 7 times 13. And 7 times 17 is more than 100, so we don't count that. So when 7 is the smallest prime, then there are 2 numbers. Now the thing is, once we get to 11, if 11 is our smallest prime factor, then any number is going to be greater than 100. So once we've gotten to this point, we see that all the numbers that we could possibly make are more than 100. That's when we stop. And we count up all the numbers that we have counted currently. So we have 2 plus 5 plus 9. And don't forget this 1 that we counted here before. And if you add all of those up, that should give you 17 numbers in total. And that's our answer.
Hey, this is Tim. Hope you're enjoying our videos. If so, you know what to do: like, subscribe, turn on notifications, all that sort of thing. But what I'd really want to invite you to do is to send us an email at media@mathleague.org. Tell us which problems you'd like to see us cover next in our video series. Take care and see you in the next video.